Hey guys, so we are getting into our next chapter. So we are into Unit 5, which is Thermochemistry. Again, a little challenging here and there. Pretty much the chemistry of heat. Now we have to start thinking about heat as being a reactant or a product, right? Because in order for reactions to happen, they have to have some sort of heat. If you have a cold environment, your molecules aren't going to bump into each other very much, right? But if you have a hot environment, those molecules are going to bump into each other a lot more, and they're going to start reacting. So we got a lot to talk about here in thermochemistry, a lot of things to get through. So let's just get to it. First of all, what is thermochemistry? Okay, it is the study of relationships between energy changes involving heat and chemical reactions. So pretty much just the study of chemical reactions and heat, okay? What we need to know is the energy. We need to know the energy. We need to know the definition of energy, right? Which is the capacity to do work or transfer heat. Right? If you got a lot of energy, you're going to be able to do a lot of work. If you got a ball that is red hot, it's going to be transferring a lot of heat to your hand, to the table, wherever that may be. What is heat? Okay, let's talk about what heat is. I keep saying that, but let's define it. What is heat? Okay. Energy. Heat is energy transferred from one object to another because of temperature difference. Alright, so guys, remember last year, there is no cold, okay? It's all heat. There's either a lot of heat or there's a lack of heat. There's no more cold. It's just no heat, lack of heat, okay? That way you can figure out or get into the state of mind of thinking how heat transfers, right? And then we got the first law of thermodynamics, right? Which energy cannot be created or destroyed, it only changes form, okay? Energy cannot be created or destroyed, it only changes form. Right? You might say that sounds a lot like matter. That's true. Okay, matter and energy pretty much are directly related. That's what E equals mc squared does. Okay, energy, all that energy at the Big Bang, at the beginning of the universe, or whatever you believe in, all the energy is still there today. Okay? And then let's get back into what we talked about a little bit last year with thermochemistry, which is exothermic and endothermic processes. Okay, so we got an exothermic process. Let's define that. That's where heat is released. Okay, heat is released, the surroundings get hotter, right? If I have a puddle of water, okay, and heat escapes, what's going to happen to that water? Right? It is going to get colder. If heat leaves, it's going to get colder, so you're going to get an ice cube. Obviously, it's not going to freeze into cube form, but you get the idea, right? So exothermic heat is leaving, endothermic heat is absorbed, okay? Heat is going into. Exo, heat is exiting. Endo, heat is going into. So let's do the opposite, right? If heat goes into ice, what's going to happen to it? Well, it's going to melt into water. All right, so we got to get that down. We got to know exo and endothermic. We know exo is exiting, so the object gets colder, surroundings get hotter. Endothermic heat is going into, the object gets hotter, the surroundings get colder, okay? So I'm going to erase this. What about a campfire? Is that exo or endothermic? I'm going to say that is exo. Heat is being released. It is heating up the surroundings. Okay. What about a liquid to gas, right? A liquid to gas, well, think. What's happened to those molecules? They're speeding up, right? In order to not be a liquid anymore, they got to speed up and move faster and faster. So that means they're absorbing some energy, or heat is going into them. All right, so that is a endothermic process. Heat's going into that liquid. It's getting excited. It's becoming a gas. And then what about gas to liquid, right? Or condensation? Those molecules are excited, but now they're getting closer to one another. They're forming a liquid, possibly even a solid. Okay, that is heat exiting them. That means that those molecules are getting colder. There's less energy, or less hot, I should say. I should follow my own rules. Okay? So there's this new thing that you're going to be hearing, which is called enthalpy. Enthalpy, not empathy, but enthalpy, which just measures heat flow. So pretty much what I want you to do is, when you hear me say enthalpy, you're thinking heat. Okay? Enthalpy is heat. And enthalpy change is denoted by, they couldn't use E because E stands for energy, okay? But they could do delta H, which H is like heat, right? So delta H is change in heat. So change in enthalpy is, so I should say enthalpy change equals delta H. So you'll see H a lot. Okay, that is just the heat release. And it's usually in kilojoules, all right? So when you have a negative H, okay? When you have a negative H, this is extremely important, and it's like a foundation of chemistry. When you have a negative H, heat is leaving the system, right? Negative, it's out of here. Okay, it's leaving. That's an exothermic reaction, okay? If H is positive, that's an endothermic reaction. It's gaining heat. It's endothermic, okay? So you'll see like negative 50 kilojoules, that's an exothermic process, okay? And usually when it's exothermic, that means it's heat is a product, okay? Right? Like if a reaction happens and the surroundings get hotter, heat is a product. It is creating heat. If it's endo, heat is a reactant, right? To have a reaction happen, it needs to absorb heat, okay? So the surroundings get colder, all right? So these two are extremely important. I can't tell you how important this is, okay? So make sure you have this down. So let's ask a couple questions about this. Let's say I have H2O liquid, and it's going to H2O gas. What would my delta H equal? Is it going to be positive, or is it going to be negative? Okay, well, let's think about this. Liquid to gas. To go to liquid to gas, I got to heat it up, right? In order to heat it up, I need to put heat into it. If heat is going into it, right, from liquid to gas, I'm going to speed up those molecules, heat it up. That's an endothermic reaction. Well, if it's endothermic, is my H positive or negative? Positive, okay? Technically, it's positive 44 kilojoules, we'll say. Okay, what if we were going from H2O gas to H2O liquid. Okay, gas to a liquid, that means that those molecules have to slow down and get closer together. Heat is going to leave those molecules so that they can slow down. So that is an exothermic reaction. That means that it's negative 44 kilojoules. Okay, it's negative, exothermic releases heat. Okay, and it's the opposite, it's equal opposite, right? The opposite of a reaction will be equal and opposite to the enthalpy. All right? So, usually what you see here, when you see kilojoules, okay, it's usually always inferred that it's kilojoules per mole. Okay, it's 44 kilojoules per mole of liquid I have. Okay, so they won't always put kilojoules per mole here, but you can always assume that it's kilojoules per mole. Okay, be aware of that, because sometimes they might say, give you a reaction, they'll be like, how much heat is produced in 2 moles of this reaction? Okay, or if I have 2 moles of H2O liquid, how much heat will be produced? Well, if they just give you 44 kilojoules, you might be like, oh, I don't know. But remember, heat is now a reactant or a product in this case. It's a reactant, so I'd ask how many kilojoules of heat would you need to react with 2 moles of H2O? You'd say 88 kilojoules, right? Because you need double. All right, it's kilojoules per mole. Alrighty, guys. So they're the same thing, kilojoules per mole for us. Next thing, I got an example for you. I have CH4 grams plus 2 O2 grams to CO2 grams plus 2 H2O grams, and all I'm going to say is that the delta HC equals negative 802 kilojoules, okay? That says kilojoules right there. Let me move it so you can actually see it. Delta H equals negative, what I say, 802 kilojoules, okay? So a lot of times you'll see it where it's delta H is on the far right side. This C here just means combustion, okay? You'll see a lot of delta H sub letters. I think there's a delta H plus F, which is heat of formation. There's a delta H S, which is like heat of, I don't know, it's something, okay? But it's still just enthalpy, okay? It's just the process it goes through. The C is there because it's combusting. All right, and then I will ask, how many kilojoules of heat are released when 25.0 grams of methane burn in air? Okay, double dotted. All right, remember guys, we are now treating heat as either a reactant or a product here. So here when it gave us 25 grams of methane, okay, we can use stoichiometry to see how much heat we produce, because heat in this case is treated just like a product, okay? Why is it treated like a product? Because it is exothermic, right? Heat is released, it is a product when it is negative. So we could pretty much just write this as CH4 plus 2O2, CO2 plus 2H2O plus 802 kilojoules. We could pretty much just say it's also producing 802 kilojoules. Okay, that was because it was negative. It's on the product side. Okay, so let's go ahead and just figure this out. We're going to do stoichiometry, right? I can't compare grams to heat right now, but I could compare moles to heat, right? Because this is technically kilojoules per mole. So let's go ahead and get those grams to moles. I got 25 grams of methane, which has a molar mass of 16. Okay, 25 divided by 16 just happens to be 1.5625 moles of CH4. Okay, and we got to do a comparison to 802 kilojoules. Well, for every 1 mole of CH4, how many kilojoules do I get? 802. Okay, 802 kilojoules. Moles cancel out. I'm left with just kilojoules. I know I'm on the right track. I'm going to go ahead and do 1.5625 times 802. So I am going to be releasing negative 1,253 kilojoules. Okay? Remember, it's negative because it was exothermic at the beginning, right? It was delta H equals negative 802. So be ready for that, okay? Let's do another example. Okay, let's say that we got NaOH, and it is reacting with H2O liquid, and then let's just say it makes, I don't know, this is a bad example. Let me do something else. Let me do NaCl. There we go. Aqueous. And it forms, this won't work either. Give me a second. I got this. Alright, so let's go with NaOH, HCl. I tried making it scientifically accurate, but it's not going to be. Alright, so I'm sorry. I'm trying to think of a certain type of reaction that will be accurate to this, but this will work for us, okay? And then I'm going to say the delta H, let's say D of dissolution this time, is, let's go, 450 kilojoules. Okay, so this is my chemical reaction, and I'm just going to say how much heat is needed to produce, let's go with 10 milliliters of water. Okay? So it says how much heat is needed to produce 10 milliliters of water. Again, we could treat heat as a product or a reactant. In this case, are we going to treat it as a product or are we going to treat it as a reactant? Well, we go ahead and we look at this and we say, hey, that's positive. We could pretty much treat this as a reactant. So I could pretty much just say, hey, let's add 450 kilojoules to our reactant side, right? It's going to be absorbing heat in order to make this reaction happen. So what we're going to do is we're going to go from 10 milliliters of water to 450 kilojoules for water. And I know some of you are thinking, 10 milliliters of water, okay, I'll change that to liters and I'll do STP, okay? Is H2O a gas? No, it's a liquid. We can only use STP. Usually it says it's at STP, and we can only use it if we're dealing with a gas. Okay, so we can't do that here. Okay, but what do I know about water? I know that water has a density of 1 gram per milliliter. So if I have 1 milliliter of water, it's 1 gram of water. If I have 100 milliliters of water, it's 100 grams of water. If I have 10 milliliters of water, it's 10 grams of water. Okay, so be ready for that. They'll throw that at you all the time. They want you to assume that water has a density of 1 and that it weighs as much as its quantity in milliliters. So let's go ahead and go from grams of H2O to heat absorbed. So we'll go ahead and we'll take 10 divided by 18 to get our moles of H2O, which is pretty much 0.56 moles of H2O. I didn't have to balance it, it's already balanced. So let's look at this. For every 1 mole of H2O created, I'm going to need 450 kilojoules. Moles cancel out. 0.56 times 450. I'm going to only need 250 kilojoules of heat. I'm going to keep that positive because it's an endothermic reaction. Okay, so I'm going to keep that positive. Alright guys, I think I am going to stop there, and I'll pick this back up tomorrow so you don't have to watch such a big video. The only thing I want to note is that, like at the beginning of this problem, I put delta H equals 450 kilojoules, okay? Sometimes they won't do that. Sometimes they'll just do it the way I had to change it. Sometimes they'll just put 450 kilojoules, okay? You'll know that this is endothermic, that's on the left side. Sometimes they might just put 450 kilojoules on the product side, and now you know it's exothermic because heat is on the right side, okay? So just be ready for that. So that's our intro to thermodynamics. Try out that practice, and have yourself a great day.